Now, on to Cartesian products. Cartesian products. Please be mindful of this. I may not be writing that much, and writing is not too good. So, I'll dictate, right? But we are doing maths. Too much, not too much of story by the way. Now, Cartesian products. Cartesian products. And for those of us that have been following our series on sets, God bless you. Thumbs up to you. God bless you. Love you. Now, Cartesian products. We say Cartesian product is a set of all ordered pairs between two non-empty sets. Listen, I repeat. Set of all ordered pairs. What do you mean by pairs? Pairs. Pairs means two things. You know what I'm saying? Set of all ordered sets, and that is why Cartesian product will exist between two sets. Cartesian product. Let's say let A be a non-empty set and B be a non-empty set. Then I'll say A cross B. That is the Cartesian product. And now the set of all x, y so that x is in A and y is in B. Set of all ordered pairs. So that's the definition of Cartesian products. If someone tell you, can you give us the definition of Cartesian product, you can write it like this, set with that notation, and you can equally tell the person, well, it is the set of all ordered pairs. Please note that word, ordered pairs between two sets, from a set to another set. Let me give you an example of it. Let's say A is a set of just elements 1, 2, and 3. And then let's say B is a set of A, B, D. And then I want to generate a Cartesian product. A Cartesian product A cross B. In that Cartesian product, what are the things that we have? What are the things that we have? Well, in that pair, I can pair 1 to A, that's a pair, 1 to B, that's a pair, 1 to D, that's a pair. So it will be 1, A, 1, B, 1, D. That's upon pairing A to the elements in B. But there's no rules that say that once A is actually is running away with any of the elements. No, A dare not abscond with any of the elements. So we're just seeing the other pairs. Now let's now go on to B, on to 2. 2 we can see have 2 pair to A, 2 can be paired to B, and 2 can be paired to C. And going to 3 3 can be paired to A, 3 can be paired to B, 3 can be paired to, oh, let me say C, it is a D, please. D, 3 can be paired to D. So this is the Cartesian products of this set, these two sets. Now please note, the Cartesian product A cross B is always different from B cross A. Again, Cartesian product operation is not commutative. Let me show you. The other is going to be A being paired to, B being paired to A. And in that order, we have A can be paired to 1, and then A can be paired to 2, is a pair, A3 is another pair, or B1, B2, B3, or D1, D2, D3. Are we together? So please be mindful of the fact that Cartesian product is not commutative. 1 comma A is different from A. 1A is different from A1. Of course, you know that. Let's say we want to take it back to the idea of geometry. You know, this is the x coordinate. The first here, that's how we say x, a set of all x comma y, x coordinate, y coordinate. Where the x coordinate, that is if it is A cross B. But in B cross A, x will be coming from B and y will be coming from A. So it's two different things. It's not equal. But well, now one thing is that the cardinality, the number of elements in our Cartesian product will be equal, will be commutative. Now listen up. The cardinality of Cartesian product will be commutative if and only if the number of elements in A is equal to the number of elements in B. Listen. I said this operation Cartesian product over two sets is not commutative. But the cardinality of Cartesian product over two sets is said to be commutative. If, write it there. I've said it earlier. I don't want to repeat myself. So write what I said now. What you add in the video, write it in the comment section. Write it in the comment section. Write what I just said. For the definition is very important because you can go into advanced mathematics and then your lecturer will come inside the class. I'm telling you, yeah, today we want to talk about relation. Before we go to relation, let's see Cartesian product. And then your lecturer will tell you, number one, is Cartesian product operation over two sets a commutative operation? You didn't thinking. But if you listen to what I just said, you can be able to tell your teacher. And why did I say it's not commutative? An operation is said to be commutative over a set if there's a backward action and then a forward action too gives the same thing. Let's assume A cross B gives us the same thing as B cross A. Now, as this one is 1 comma A, this one is 1 comma A, and this one is 1 comma. In fact, maybe here we now have a B comma 1. Let's assume this one is 1 comma B. The order does not matter. Get it right. This one doesn't mean that if, let's say, we have the same thing and the same thing here, but then this one is here, this one is here, and then this one is maybe something that is exactly like this is here. The order doesn't matter, the placement doesn't matter. So far, they are the same thing. It's not like, again, I've said that A comma B is different from B comma A. But that I have an A comma B and then maybe I have an A comma B and the two is the same, it's still A comma B. So we notice that it's not equal. The only thing that will make it happen like that is if I'm trying to get Cartesian product of a set onto itself. The Cartesian product of a set onto itself. The Cartesian product of a set onto itself. That is when I can now say, okay, now you know that in that situation, now take a look at this set. This should be 1, then I can have a 1 comma 1, and then 1 comma 2, and then 1 comma 3, and then 2 comma 1. And then 2 comma 2, and then 2 comma 3, and then 3 comma 1, and then 3 comma 2, and then 3 comma 3. I'm not putting comma in between it, please put comma in work to separate it. And then this I will say yes. So since it is A onto itself, if I have to do A onto itself again, I will get the same thing. So it is if it only exists that way that it will be commutative, it will be commutative only if it is a Cartesian product of a set onto itself. And it's purely under definition. Now, but let's ask, is the cardinality, another question, is the cardinality, and I think that was the question I asked earlier, but I can't remember, is the cardinality, the operation of cardinality of Cartesian products, you know, cardinality of a set, I've told you that cardinality of a set is the number of elements in the set. Now, that operation, cardinality of Cartesian products, is it a commutative operation? Drop your answer in the comment section. And if it is, at least give an example to buttress your point. The person that get the right answer, the first person, because we know some people come and copy, the first person that get the right answer, thumbs up to you, thumbs up to you. That will shout out to you. Now let's now see something relatively cool. Relation. Now what's a relation? Well, let's say a relation R is a subset. It can be proper, it can be an improper subset of Cartesian products. The relation R between A and B is a subset, either a proper or an improper subset of the Cartesian product between A and B. Okay, let's say set A is a set of all elements 1, 2, 3. And set B, let me use another thing, X and Y. By the way, how many elements should be in the Cartesian product? If you don't want to solve it out, you don't want to list the elements, just say the cardinality of the Cartesian product is actually the cardinality of A cross the cardinality of B. Now, how many elements do we have here? 3 times. How many elements do we have here? 2. So the cardinality is what? 6. We have 6 unique and distinct elements in the cross product of A and B. The Cartesian product, of A and B. Now, the Cartesian product, let's list it out. Let's list it, sorry. So now, it is A pair to B. Set of all other pairs A to B. Set of all other pairs is A to B, not B to A. Please note, A to B, not B to A. So, on A to B, we have A1 to X, and we can can still have a 1 to y. But on A, 2 to x, we can still have a 2 to y. Or on that, 3 to x, and we can have a 3 to y. So let me have this bracket. So that is it. How many elements do we have? 1, 2, 3, 4, 5, 6. That's what we said. 3 cross 6. So note that for free. So if someone asks you if the cardinality of a set is 5 and the cardinality of another set is 60, sorry, 6. Sorry, and the cardinality of another set is 6. So you can say, hey, how many elements will be in the Cartesian product? In the Cartesian product, not the relation. Only if you want to ask me the number of elements that will be in the relation, I need to ask. Well, you want me to tell you the number of elements in the relation? Is the relation equal to the Cartesian product? That is the only time I can tell you the number of elements in the relation. Only if you give me the relation, then I can tell you the number of elements. But if not, if you want to make it an abstract question, give me more information about it, so that at least I'll be able to give you an answer. Now let's come back to this place. Now, if I don't want to do a relation from here, I can build a relation of just relationship of 1 to those sets. I can build a relation as 1x and 1y only. This is a relation. And obviously this relation is a subset of this set. So that's why my relation is a subset of the set. A relation is a subset of the set. A relation is a subset of the set. All together here now, that is it. So that is what the idea of relation is all about. A relation, in fact, everything here is another relation. You get what I'm saying? So I said subset of a relation is a subset of a Cartesian product. Subset of a Cartesian product. Subset. Now it cannot be a proper subset of a Cartesian product between two sets, or it can be an improper subset of Cartesian product between two sets. Like this relation, let me say relation R1 is a proper subset of Cartesian product between A and B. And this one is an improper subset of the Cartesian product between A and B. Because all the elements in the Cartesian product is actually in the relation 2. All together here. Now from there we'll go to a very much beautiful series. Before we go to that series, I want to ask a question. What's the question? Please be honest. Drop your answer in the comment section. Be honest about yourself. And you know, as we usually do, the person that gets the right answer, big shout out to you. Now, what's the question? Okay, let me read juicy. The question is, are all relations a Cartesian product? Are all relations a Cartesian product? Are all Cartesian products a relation? Number 1, are all relations a Cartesian product? Number 2, are all Cartesian products a relation? Now, when is a relation said to be a Cartesian product? Or is it not possible at all? Okay, that is not possible. When is a Cartesian product said to be a relation? And finally, are all relations mapping? Are all relations mapping? There are 5 questions. Number 1, are all relations Cartesian products? Number 2, are all Cartesian products relation? Number 3, when is a Cartesian product, if not all, right? If not all. If number 1 and 2 is yes, then you don't have to answer number 3 and 4. But if number 1 and 2 is no, okay, when is a relation said to be a Cartesian product? Or when is a Cartesian product said to be a relation? And finally, are all relation mapping? If no, when is a relation said to be a mapping? Answer the question, drop the answers in the comment section. We take the time to go through all your responses and to tell you the person that gets it. Thank you.